In lecture 6, we talked a lot about work and heat, and at the end of it, we were talking about the heat capacity, which is the ability of a material, a system, however complex, to absorb heat and in the process change temperature. The heat capacity is heat absorbed per unit change in temperature. But we never said anything about what kinds of molecular properties down at the microscopic scale are responsible for a heat capacity. And so we never talked about what kinds of materials might have high heat capacities, what kind have low heat capacities, and so on. So what is the molecular origin of C, of heat capacity? Here's the basic bottom line. The heat capacity is created or controlled by the number and size of places in molecules and the interactions between molecules where energy can be stored when the temperature changes. Let's look at some examples of how that works. There's two kinds of energy, kinetic energy and potential energy. And the translational degrees of freedom, that is, the ability of a molecule to move freely in space, includes a type of energy, kinetic energy, translational kinetic energy, and when the temperature increases, goes from lower to higher, the average velocity, and therefore the average kinetic energy, increases also. And so, in the course of warming things up, some of the energy that went into the system is stored in the form of kinetic energy in all the molecules. Same for rotations and vibrations. Rotation is velocity, or rotational kinetic energy is velocity, but for rotational motion instead of translational motion. And when the temperature increases, that rotational velocity increases, and therefore the kinetic energy increases. Likewise for vibrations, there's a kinetic energy, there's a potential and kinetic energy component involved in vibrations, but the kinetic energy component increases when you increase temperature, and so that's another place energy can be stored. For potential energy, what potential energy means in a molecular context is basically either bond stretching. You're taking a shorter bond and making it longer, and that requires energy. You have to put energy into the molecule to do that, so we're storing energy when we do that. Or else bond breaking altogether. You have some kind of bond, let's say a hydrogen bond is kind of the most common case. That gets broken when the temperature gets a little bit higher, or statistically there's a tendency for it to get broken. So let's suppose 90% of the bonds are formed when you're at lower temperature and only 70% when you're at higher temperature. Still, most of the H bonds are there, but fewer of them than were present at lower temperature, and so those broken bonds also represent stored potential energy and contribute to the heat capacity. So these are the kinds of features in the molecules that give rise to high heat capacity. I think one of the materials that has, or substances that has the highest heat capacity of all, it may be the very highest, I don't know, is water. And the reason for that is its ability to form hydrogen bonds. It's exactly this process where hydrogen bonds tend to break as you raise the temperature that gives rise to the high heat capacity of water. There's another place where the heat capacity behaves in a way that's important to understand, and that's when you get some kind of phase transition. So a melting transition or a vaporization transition. What happens there is you go from an ordered crystal to a disordered but still densely packed liquid to very low density gas. And in the process, the interactions, the sticking interactions, or if you like, the bonds, quote unquote, between the molecules, these aren't chemical bonds, but just sticking interactions, which we'll kind of call bonds, they get weaker, right? When you're going from this case over here to this case over here, they're weaker. That means you've kind of you've either stretched or broken a whole bunch of interactions that were there before. And that means the potential energy is higher for this case, and therefore you've stored some energy. And the same thing is even more true when you go to a gas, of course, where all the close interactions between the molecules are broken, and the molecules basically become all independent of each other. Well, the thing about phase transitions is that they're cooperative. What that means is you get an all or nothing effect. When this happens, you don't just get one or two molecules that get disordered, the whole thing goes disordered at once. And likewise, when this happens, you don't just get a few molecules loose in the gas phase, everything goes at once. And it happens over a temperature range that's extremely narrow. So if you think of the heat capacity as heat per unit temperature, this delta T, this heat is large and this delta T is small or approaching zero, and the heat capacity goes very high. There's a spike in the heat capacity. If you were to plot that, so if you plot the heat capacity versus temperature as you're going through phase transitions, you'll see a slow rise in the heat capacity when you're in the solid phase. And then right at the melting transition, you'll see this spike that represents this effect right at the melting point. And then you'll see another slow rise in heat capacity as the liquid warms, and then another spike where the liquid boils finally, and then a slow rise in heat capacity after that as you continue to warm the vapor. We see this kind of effect especially in biological settings in these sort of low cooperativity or semi-cooperative transitions. DNA melting isn't really melting in the classical sense, but it is cooperative. It's a bit of at least a partially all or nothing kind of phenomenon. So you get the same kind of behavior here. It just isn't as pronounced. So if this is the melting point for DNA, the definition of the melting point, in fact, is that you see this bump in the heat capacity as you go over from the double-stranded form over here to the single-stranded form, and the DNA melts and becomes a random coil. And the same thing is true for protein unfolding. If you have a protein that's folded up, pretty tight, coherent structure, and then it unfolds to a random coil, that's also a mostly cooperative process, and you'll see a bump in the heat capacity versus, this is heat capacity here, versus temperature as a result. All right, and that's the heat capacity. Now let's return to some of the formal structure of thermodynamics. An important feature, an important idea in thermodynamics is the idea of a state function. Here are some state functions. Pressure as a function of mole number, temperature, and volume. I can write it formally in a mathematical sense this way, right? Pressure is some function. It's this function, in fact, exactly. But it doesn't matter for the moment what that function is. It's some function of temperature and volume and mole numbers. And therefore, it's a function of the state of the system. Remember, these three numbers in this case for a single pure substance, that's the state of a thermodynamic system. And so this is a function of the state, and so it's a state function. Same thing for energy. It's also a function in this case of mole numbers and temperature. The chemical potential is a function of T, V, and N. They're all state functions. We haven't talked about any of these guys yet, but they're coming up. The enthalpy, the entropy, the Gibbs free energy, and the Helmholtz free energy. They're all functions of the state. And you notice the variables are changing here, but that doesn't matter. You can always change the variables. What stays the same is the number of variables in each case. For a single pure substance, there's always three. And therefore, each of these represents a different way of expressing or representing the state of the system. So all these are state functions. And that's what I'm saying down here. A state function, or sometimes a similar thing is called an equation of state, is some function of the state of the system. State functions are very important and very useful. They're widely used in essentially almost every thermodynamic calculation. And the reason is this. Let's suppose you're carrying out some process, and you do it by two different paths. So in this case, there's a path, let's call it path A here, and this one called path B. So we're changing from state 1 to state 2 up here, down here. And you can go by path A or you can go by path B. Because the energy is a state function, it doesn't care about the path. It cares only about the initial state and the final state. You have to know those two, and those two matter. If you change either of those two, delta U will change. But not the route by which you got between those two states. the path doesn't matter for a state function. And that's true for all these guys. So pressure, enthalpy, Gibbs free energy, chemical potential, all those guys are state functions. All you need to know, you don't need to know the path in order to do those calculations. All you need to know is what's the initial state, what's the final state, and you can calculate the change. On the other hand, work and heat are not state functions. That means that if you have two different paths by which you get from state 1 to state 2, and you do a calculation to get the work, for example, then when you're going by this path, on this PV diagram, the work, remember, is the area under the curve. So here's the work for path A. It's this dark gray area. But if you go by this path, the work is also the area under the curve, but now it's this light gray area plus the dark gray area underneath. It's the whole zone. And so obviously the work by path B is much greater than the work by path A. And that means the work does depend on path. You have to know the path in order to calculate the work. And if that's true, and if it's also true that the internal energy doesn't depend on path, and if it's true that the sum of the work and the heat is equal to the energy, then you can show, well, you can rework this a little bit to show that the difference between the work for path B and the work for path A, that's the area in the little football zone here, that's not zero. That difference is not zero. And that has to be equal, according to all this stuff up here, that has to be equal to minus the difference between the heat on those two paths. And that means the heat on those two paths is also not the same. And therefore, heat is also not a state function. Heat and work are really the only things in thermodynamics that aren't state functions. Everything else is a state function. So the distinction is a little bit formal. We talk about path functions and state functions, but really we could just talk about heat and work and everything else. Heat and work are not state functions. Everything else is. All right. Now let's do an example. We've learned a bunch of stuff. Let's do at least a semi-complicated example. And so let's consider, first of all, an ideal gas. Those are much easier to deal with than anything else. And I'm going to consider a monatomic ideal gas. We'll see why that matters. It controls the heat capacities, actually. Let me just say it. For a monatomic ideal gas, the CV is 3/2 NR, and the CP is 5/2 NR. So by saying it's monatomic, I'm basically giving myself knowledge of the heat capacities, which we'll need. All right, so I start with state 1 here. I start with a certain external pressure. I start with 1 mole of that stuff, 1 liter, temperature of 300 K. I hold things at constant pressure by some means or another. And I heat the system until the piston has expanded a little bit, the volume has gone to a little bit more than a liter, and the temperature has gone up to 350 K. But the pressure is still whatever it was to begin with. Here it is calculated down here, right? Given these things up here, I can calculate the pressure, and it's 24.6 atmospheres. It's still 24.6 after I heat because I allowed the system to expand as I was heating. Then in the next step, I compress, and in this case, I compress at constant T. So this is, and it's reversible, so this is a reversible isothermal compression of an ideal gas. We know how to deal with that. At the end, I've compressed back to the same volume I was in, and the temperature is higher, though, because I heated here and I never cooled back down, kept the temperature constant. So as I was compressing, the temperature wasn't changing. It's still at 350 K. And as a result, at the end, the pressure inside is a little bit higher, too. Instead of 24.6, it's 28.7. All right, let's do the calculations now. These 2 steps here correspond to 2 steps on my PV diagram. This is the first step here, and this is the second step here. This is the isothermal step. This is the constant pressure step. You can see it's constant pressure, right? Pressure is not changing. Volume is changing. And then we're going to consider a second path just to illustrate the fact that the energy, the overall energy, doesn't depend on path, but the heat and work do. So here's the second path. I call it path B here. This is path A. The overall, both steps together are path A. Here's only one step, so that's path B. I'm going to go straight. Instead of going around this funny loop here, I'm going to go straight up from the initial state to the final state just by heating. And here's what that process looks like, yeah, in drawings anyway. So I pin the piston in place, so no matter how much I heat, even though the pressure is rising in here, it can't expand. And then I just heat, that's it. And I start at 300, I end up at 350. All right, I don't know what that is. Oh, that's a calculation I was doing and forgot to erase. Let me erase it now. All right, that wasn't supposed to be there. All right, so path 1, or I called it path A up here. Let's call it path A. And do I call it path B? Path B down there, yeah, okay. So path A, in step A1 is the first of these guys, this part of path A, at constant P. So since we're at constant P, work is equal to minus P delta V. That's 24.6 atmospheres times a delta V, right? We went from 1 liter to 7/6 of a liter. So that's a 1/6 liter change. So that's what that is. And that gives us minus, right, because of the minus sign here, 4.1 liter atmospheres. Not a great big change, but not a great big amount of work, but some. And negative, notice, it's good in these early examples especially to notice when the piston expands like that, it's doing work on the surroundings. That means the system is losing energy. That means the work will be negative. Okay, the heat is mole numbers times heat capacity. Heat capacity at constant pressure, right? Because this is a constant pressure process, times the temperature change. That's 1 mole, 5/2 R. Here's where I need the heat capacity at constant pressure. That's why I needed to say it was a monatomic ideal gas. And then a temperature change from 300 to 350 is 50 degrees for an overall change of heat of 10.26 liter atmospheres. I'm using these liter atmosphere units. They're really, ugly, and you should never actually publish anything in liter atmosphere units, I don't think, but it's fine for this example. All we want to do is see if things are the same or not, so any units are fine. Delta U now is equal to the sum of these guys, right? So I add both of these together, and that gives me 6.16 liter atmospheres. Notice that in this case, I'm calculating delta U by specifically adding together W and Q. But I can also calculate delta Q by using this equation of state. 3/2 nR delta T is equal to delta U. So plugging in the numbers, gas constant in liter atmospheres per mole degree Kelvin, and I get 6.15 liter atmospheres. That's the same to within round-off differences. So I've confirmed that the energy is the same on the two paths. Well, the energy is the same whether I do it. Yeah, actually, this is actually the energy change for this path as well. So I guess we'll do it again downstairs, but I guess I actually have proved that the energy is the same on the two paths. That's one of the purposes of this whole example. But I've also shown that I get the same answer either from the formula or from adding together heat and work. You can see this calculation was just way easier than doing the heat and work calculations, right? The heat and work calculations, because they depend on path, are always more difficult. So if you can get away without doing them, if you don't actually need heat or work, if all you really want is energy, try your best to avoid having to do a heat and work calculation. It's a lot more work. All right, for the second step, it's a reversible isothermal compression of an ideal gas. That's the formula. We derived that earlier. Plugging the numbers in, I get 4.43 liter atmospheres for the work. In this case, because there's no temperature change, the delta U for an ideal gas without a temperature change is always 0. You can see that in this formula, right? If delta T is 0, then delta U is 0 too. But delta U has to be equal to Q plus W, so that means Q has to equal minus W, and therefore Q is minus 4.43 liter atmospheres. All right, so adding everything together for the full path A, not both steps together, minus 4.10 for step 1, 4.43 for step 2, and almost no work at all for the overall process, just 0.33 liter atmospheres. For the heat, 10.26 for step 1, minus 4.43 for step 2, for an overall of 5.83 liter atmospheres. And finally, yes, adding up the work and the heat for the overall process now, it's 6.16. And that's, of course, exactly what we got up here already, and what we got up here, too, for that matter. All right, now for path B, the straight path, the simple path, this one here. Well, what's the work? There's no volume change on that path, and delta V is therefore 0. Therefore, the work is 0. That means the heat is equal to delta U, which is 3/2 nR delta T. Notice that this is also CV delta T, right? If I was calculating, here I'm really kind of thinking of calculating delta U, but if I was thinking of calculating heat, I would use CV delta T, and then for a monatomic ideal gas, CV is 3/2 nR, and so I would get the same formula either way, whether I think I'm calculating heat or whether I think I'm calculating energy, I get the same thing, and 6.16 liter atmospheres is the answer. Okay, that's a relatively complicated, sort of medium complicated calculation of this sort. They can be a lot more complicated. You'll see if you go looking through the exams from previous years that these kind of problems where you do some kind of calculation of heat and work and other thermodynamic variables around some path are very popular for exam 1. I won't promise that there'll be one on exam 1, but boy, there probably will be. All right. Now, we've talked about state functions. Really, the only state function that or kind of big state function that we've talked about so far is energy. Now let's define a new one. It's called enthalpy. The enthalpy is defined, this is a definition here, is defined to be the energy plus the quantity PV. And again, yes, it's a state function. How can you tell that it's a state function? Well, that's a state function. P and V are both state functions. It's a combination of state functions. It's got to be a state function itself. And like I said, you can always tell it's a state function because it's not heat and it's not work. Therefore, it's a state function. Okay. If I want to calculate the change in the enthalpy, that's the same thing as the change in the energy, plus the change in this overall quantity PV. And this formula is good no matter what kind of process we're talking about. But very often when you're talking about enthalpy, what you're really interested in is a constant pressure process. Enthalpy was essentially invented to make constant pressure process calculations easier. So, almost always when you're interested in enthalpy at all, you're interested in a constant pressure process. In that case, this pressure can be factored out of this difference or this delta, and you get delta U plus P delta V. Well, P delta V is what? For a constant pressure process, work is equal to minus P delta V. And so this is just minus work. And so this is really delta U minus work. And that's heat, right? It's heat for a constant pressure process. And so this business, this relationship right here, was, I think, historically the primary motivator for even defining this otherwise kind of funny quantity, enthalpy. Why would you want to combine energy with this quantity after all? Well, this is why. It makes it easier to calculate work, heat changes. Heat changes are notoriously kind of tricky to do. But in this case, notice this is a state function up here. That means the reversible heat for a constant pressure process. I say reversible here, and I should have emphasized that before, because it is only for a reversible case. The heat change for a constant reversible process, constant pressure reversible process, is a state function. So there are cases like this one, let me not confuse people, where for certain special cases, the heat or the work actually are state functions. For example, if Q is equal to 0, then delta U is equal to W. Delta U is a state function, so in that special case, W also must be a state function. So there are cases where heat and work can be state functions. They're just not state functions in general. All right, we'll stop there and pick up with the next lecture later.